Welcome to everyone. I'm Dr. Godan Raman, Department of Mathematics, SRM Institute of Science and Technology, Katangalatun. Today we have discussed with a single server finite capacity problem. Here I have mentioned some important formula. Probability of no customer in the system. Probability of no customer in the system. Here we have discussed with two cases. One is arrival rate and service rate not equal. We can use the first formula. And second one, arrival rate and service rate is equal. Then we can use other formula is 1 by k plus 1. Then probability of n customer in the system. Here also we have discussed with the two cases. When the arrival rate and service rate is not equal, then arrival rate and service rate is equal. Here also the effective arrival rate formula is given. And then average number of customer in the system is LS, because we have to find out for the number of customer in the system. Here again two cases we discussed with arrival rate service rate is not equal, we can use the first one, and arrival rate service rate is equal, then we can use second one. Little formula, the little formula is what? Generally the queuing system is answer two question. One is the number of customer and other one is waiting time. So number of customer is where? Number of customer in the system is a LS, number of customer in the queue LQ. Then waiting time in the system is WS, waiting time in the Q is a WQ. So little formula, if formula is what says that if you know anyone, so is related to the other one, that is means you know LS, using the LS to find the LQ, then LS LQ you know that, then using this to find WS WQ. That is a very simple cases. So now next one, number of customer in this system LQ. So LS you know that, just substitute LS value to find the LQ. Again the WS, so awaiting time of customer in the system, so you know the LS already, right, the formula, and then LS substitute here we are finding WS, similar way of a waiting time customer in the queue, so WQ. The problem here it mentioned that patients arrive at a clinic according to a Poisson distribution at a rate of 60 patients per hour. The waiting room does not accommodate more than 14 patients. Investigation time per patient is exponential with mean rate of 40 per hour. Determine the effective arrival rate at the clinic. What is the probability that an arriving patient will not wait? What is the expected waiting time until a patient is discharged from the clinic? So first of all, the given problem, after reading the problem, just you check the given problem is single server or multiple server. Here they mentioned that the patients to meet, just patient to go to the doctor. So we are here that we are assume that doctor is single server. And then we can check the capacity level. This capacity level is a finite capacity or infinite capacity. Because of the given waiting room is allotted. So waiting room allotted, only 14 patients are allowed the waiting room. If more than 14 patients are coming for the service, they are not allowed, they are waiting for outside. Therefore the waiting room is fixed, the capacity level is finite. Single server finite capacity, okay, so fixed. Then next what we are going to do that, first of all you check what is the arrival rate. Arrival rate is customer arriving for service. So arrival rate is what? 60 patients per hour. Therefore the lambda value 60 patients per hour. Then what is the investigation time? Investigation time is nothing but is the service rate. The service rate is mentioned there 40 per hour. So mu is 40 patients per hour. Then the capacity. The capacity here I am taking K. K is given 14, but here I taking for 15. Why? Because of reason. In this problem, the capacity 14. Because of waiting room allotted only 14 patients, but the investigation room, that is a doctor room, one patient is there. Therefore totally K is a 15. So 14 patients waiting room and one patient under the investigation room. So this is the K value 15. Then what is the first question? Effective, determine the effective arrival rate at the clinic. So effective arrival rate lambda dash. So nothing but, so P naught I mentioned that no customer in the system. That is a minus. So no customer or no one is wait here. But 1 minus P naught is what? When the customer is in the service. That is a server is busy. So mu is a service rate. So effective arrival rate when you to reach here, when service rate it depend on the BC for the server. Therefore lambda dash is mu into 1 minus P naught. So now first you find the P naught, probability of zero customer in this system. So P naught we have two cases, correct? One is when arrival rate and service rate is not equal and the arrival rate service rates are equal. But in this problem the lambda is a 60 value and mu is a 40. Therefore the arrival rate and service rate is not equal. Therefore I am using the first formula. The first formula is given here. Just substitute the lambda value and mu value. Now I am getting the value P naught 0.0007624. Now you substitute this P naught value to put in the effective arrival lambda dash. So mu value 40, then substitute P naught value. Now I am getting the lambda dash is effective arrival rate is 39.9695 per hour. And what is the next question? What is the probability that an arriving patient will not wait? So arriving patient will not wait because there is no customer in this system. So no patient in the clinic. So no patient in the clinic is a P naught. So already we know the answer P naught. So just directly substitute P naught value. Then what is the third question? What is the expected waiting time until patient is discharged from the clinic? So here they mention waiting time. So waiting time is a W. Then discharge from the clinic. Here clinic is the system. So WS. So you find that WS is equal to LS by lambda dash. So now already we know that what is the LS value and lambda dash. Just substitute LS and lambda dash. But LS already given the formula for the two cases. Arrival rate, service rate is not equal. Arrival rate, service rate is equal. But here is not equal. Therefore I am using the first formula. Then substitute lambda value, mu value, k value. After substituting, LS is the 14% per hour. And WS already I know the lambda dash value. Just substitute LS and lambda dash. The WS is 0.3503 per hour for the waiting time until the patient discharged from the clinic. Okay. And next problem. In this problem, so already I mentioned that the important formula, right? So in this important problem, so formulas we have discussed two cases, but in this formula we used for the both the cases. Okay, so first one, at a railway station only one train is handled at a time. Okay, the railway yard is sufficient only for two train to wait while other is given signal to leave the station. Trains arrive at the station at an average rate of 6 per hour and the railway station can handle them an average of 12 per hour, assuming Poisson arrival and exponential service distribution. First question, find the steady state probabilities for the number of train in the system. Second one, find the average waiting time of a new train coming into the yard. Third one, if the handling rate is reduced to half, and what is the effective of the above result. So first you read the problem, then after that you decide that what is the given. So now single server, first of all you check whether the problem is single server or multiple server. Now here is mentioned that at a railway station, so they are handling for the railway yard, right? So here only single server. Railway station is a yard, we have mentioned that, therefore is a single server. And capacity level, the capacity is what mentioned that one train is handled at a time. So investigation place one train is available and two train waiting for the signal. So therefore two train waiting for the signal. The capacity is mentioned that, so finite capacity. Then what is a lambda value? Lambda is a customer arriving for service, that is a train arriving for service. So 6 per hour. So lambda is a 6 per hour. And investigation timing, mu value, mu is 12 per hour. Then capacity 3, I mentioned already that one train is investigation place and two train waiting for the signal. Therefore we have two train waiting and one train investigation place. Therefore K is a 3. Then what is the first question? Find the steady state probability for the number of train in the system. So number of train is a Pn, probability of n number of customer in the system. So n number of customer in the system we have discussed with here, n is a 3 because of reason one train, second train, third train, correct? So you just find out the value Pn, then substitute n is 1, 2, 3. So P1, the steady state probability for the number of train in the system is P1 is the first train, P2 is the second train, P3 is the third train. So how to find out P1, P2, P3? So Pn, you write the formula for Pn. So Pn is nothing but lambda by mu whole power n P naught. Okay, so when is lambda not equal to mu? Then P naught value, substitute just P naught value. So here lambda not equal to mu, so I use the first formula. Just substitute lambda mu k value, then P naught 0.5333. Then P1, okay, What is a P1? So Pn value we know that. So Pn is nothing but 6 by 12 whole power n 0.5333. Now you substitute n equal to 1. Then you are getting for P1, first one. Okay. And P2, P3. So n value just substitute 1, 2, 3. Then what is the second question? The second question, find the average waiting time of new train coming into the yard. So new train, so waiting time. Okay, waiting time is Ws. So Ws equal to Ls by lambda dash. As usual, Ls is what? When lambda not equal to mu, then we can use this formula. Substitute lambda value, mu value, k value, and then getting the value what? The answer is 0.7333 per train. And then substitute this L value to in the Ws, and before that lambda dash. Lambda dash is what? Mu into 1 minus P naught. So substitute mu value, P naught value, then lambda dash is 5.6004, then Ws value 0.1309 per hour. So this is the average waiting time of new train coming into the yard. Then what is the third question? The third question is, if the handling rate is reduced to half, that's the meaning. Handling the rate is reduced means service rate. You just reduce the service rate because of the lambda is 6, mu is 12. If you want to reduce this service duration rate, it's changed with 12 to 6. Therefore lambda is 6 and mu is 6, then k is 3. So using this 3 value should find the previous effect of the result. The previous question is what? The find the steady state probability for the number of train in the system. How to find this? So first Pn. Find the Pn is what? Pn, when the arrival rate, service rate are equal, then we can use the formula 1 by k plus 1. Then what is the k? 3. Just substitute Pn equal to 1 by 4. So here no n in right hand side value. Therefore just substitute n equal to 1 or 2 or 3. Any value for substituting n, the answer should be the 1 by 4. Therefore P of 1 is 1 by 4, P of 2 is 1 by 4, and P of 3 is 1 by 4. Then what is the second question? Find the average waiting time of a new train coming into the yard. So that is a Ws, Ls by lambda dash. Then Ls, in Ls formula is the average number of customer in the system when the arrival rate and the service rate is are equal, because lambda 6, mu 6. So when is a 6 means k by 2. So Ls equal to k by 2, k value you know that, just substitute k value 3, then 3 by 2 is a 1.5. Then lambda dash again mu into 1 minus P naught, so 4.5. Now substitute Ls lambda dash in this Ws. The Ws is nothing but 0.3333 per hour. So this is the average waiting time of new train coming into the earth. This problem used for two cases. Case 1 is what? Arrival rate, service rate is not equal. Then arrival rate, service rate are equal. So thank you so much for this lecture.